All right, in this video we're going to go over the parallel circuit. So we just covered the series circuit in the last video. Now we're going to talk about the parallel circuit. So you can see the difference here is that there's more than one path, right? Remember, in the series circuit the current is the same everywhere. Well, in this circuit the current is going to be different everywhere, but the total current will equal the sum of the branch currents. So with that being said, what is a branch current, or what is a branch? A branch is you can tell a parallel circuit because there's a fork in the road, right? So right here, current's coming into this point and current leaves out of it in this direction and in this direction. So if we ever have a fork in the road, you're definitely looking at a parallel circuit. Well, a branch is just one of the pathways that the fork makes, right? So we've got a branch here, here's a branch, and here's a branch. So this parallel circuit has three branches, right? So if I find the current here, and the current here, and the current here, and I add them all together, so I add this current, and add this current, it will be equal to the total current of the circuit. All right, so let's talk about how we do that. Well, first let's talk about one more thing. So with the series circuit, we shared the voltage, right? Every resistor only got a portion of the total voltage. So in this circuit right here, we know the positive terminal is the long dash and the negative is the short dash. So we have 12 volts up here and 0 volts down here, right? Well, this makes it a little easier, if we're trying to find the voltage drops, because we always know the voltage drop on a parallel circuit. So if I have the voltage from here all the way from here to here, this entire area of the circuit is 12 volts, right? And on this one, on the negative terminal, if I go all the way here, all the way across, the entire voltage from here to here to here to here is 0 volts, right? So every one of these resistors gets the full push. That's why there's going to be much more current. So I use the exact same resistors that we did in the series, but they're configured in parallel instead. So let's see if there's going to be more current or less current. So we do get the full push, so obviously we're probably going to have less current, right? So again, if I put my multimeter on the wire right here, so I put my multimeter here and I put my multimeter here, what should the multimeter read? Remember, it reads the difference, right? The potential difference, or the voltage. So what's the difference in voltage between here and here? It will read 12 volts. So we always get the full voltage drop across a parallel circuit. Let me ask you a little bit of a tricky question. So what happens if I put my multimeter here and here? So here's my multimeter. What will my multimeter read this time? Go ahead and think about it for a second. All right, so if you got 0 volts, you have the right answer, right? Because a multimeter reads the difference between two voltages. Well, the voltage here is 12 volts, and the voltage here is 12 volts. So what's the difference between these two is zeros. So perfect. Hopefully you got that, but if not, you'll get it the next time. Okay, so here's our circuit. What are we trying to do? We're trying to find the current. So in this one, the total current is a little tricky, because the total current is the currents that's coming in and out of the battery, right? So I'm just using conventional flow here, positive to negative. So this is the total current over here. It's called the source current or total current, but it's what's coming in and out of the battery. Once this total current hits this node, a node is just where wires come together. So once it hits this node, then it splits into two, right? So we're going to figure all that out. So let's talk about it here. So there's two ways to do it. I'm going to show you both ways, but the easiest way that I like to do it for parallel circuits is just find the branch currents. So can we find the current in this branch right here? Well, first off, do we know the voltage drop across this resistor? So what is the voltage drop across that resistor? Good. You should have said 12 volts, right? Because it gets the full voltage drop. So if we know the voltage drop from here to here is 12 volts, and we have the resistance, can we solve for the current using the Ohm's law triangle? Yes, right? So we'll just use our triangle again. We want the current, excuse me. We know the voltage is 12 volts. We know the amps. The resistance is 1 ohm. So we just use our triangle, cover up the I. 12 divided by 1 is 12 amps. So we already have way more current than we did with that series circuit, right? So perfect. All right, so now we know the current in this branch right here. Can we find the current in this branch? Well, we're just going to do the same process, right? So we're going to use our triangle. We do know the voltage drop because that's just given now. If you know parallel, you know the full voltage drop. So what's the voltage drop? It's 12 across that resistor. So on this side, there's 12 volts. On this side, there's 0 volts. It gets the full voltage drop. Every branch does. And we know this one has 2 ohms, right? So what is the current? 12 divided by 2 is 6, right? And we're just going to do it one more time for this branch here. So we'll use Ohm's law again. I think we kind of got the hang of it now. What is the voltage drop across here? It's 12. What is the resistance? Is 3. So what is the current? 12 divided by 3 is 4 amps. So I like to do it like that. It's actually, for me, it's a little quicker because then I know, well, what would be the total current? Well, if there's 4 amps here, 6 amps, and 12 amps, I'm going to go 12 plus 6 is 18 plus 4 is 22. So I know that there's going to be 22 amps coming in and out of this battery. So let's talk about that for a second. So here's an example because it's kind of sometimes it gets tricky for people to understand. So here's an example of a water tower. This is in San Marcos where we're located. So we have this water tower and supplying water to these pipes, right? So this pipe has 3 gallons per minute coming out of it, right? And then we have another pipe and it has 1 gallon per minute. So think of a gallon of volume of water coming out every minute, right? 2 gallons coming out of this pipe every minute. All right, well, let's just take this first pipe right here. So this portion of the pipe, if there's 3 gallons per minute coming out of this pipe, then how many gallons per minute are flowing in this branch or this leg of the pipe, right? Well, mass can't just be created out of anywhere, right? So if there's 3 gallons per minute coming out, that means there's 3 gallons per minute in that pipe right there. All right, well, what about this pipe? There's 1 gallon per minute coming out of this pipe. Therefore, how many gallons per minute have to be within this portion of the pipe right there? Well, that would be 1 gallon per minute, right? 1 gallon per minute. Okay, well, these 2 pipes can come together right here. Well, there's 1 gallon per minute coming out this way and 3 gallons per minute coming out that way. How many gallons per minute are in this portion of the pipe? Well, it will be 3 gallons because it's supplying 3 gallons for this side and it's supplying 1 gallon for that side per minute. So this would be 4 gallons per minute, right? But we have a third leg of this pipe or the branch, one more branch, right? Well, we have 2 gallons per minute coming out of the pipe. Therefore, how many gallons per minute are right here in this side of the pipe? 2 gallons per minute. So we know there's 2 gallons per minute here, 4 gallons per minute here. Therefore, let's just think how many gallons per minute would be in our source pipe or our total flow rate. It would be 6 gallons per minute. So current works the same way, right? If there's current in this pipe, it has to be supplied from somewhere, and it's going to be supplied from the battery, of course, but it's all going to be in that source wire, or that source current, the main wire. So in this example, we knew we had 22 amps coming into coming in and out of this battery, right? So 22 amps are coming right here, 22 amps. We know that here it hits and splits, right? We know 4 amps are coming down. Therefore, how many amps must be in this wire right here? Well, that would be 22 minus 4 would be 18 amps, right? And that makes sense. So then there's 18 amps, which we know amps is just electrons moving, right, in a wire. It's coulombs per second. So we have 18 amps coming in to this node, this fork in the road, and we know 6 amps are coming down. So how many have to be going in this wire? Well, we know it's 12. And that makes sense. There's 12 amps in this branch right here. So then the 12 amps comes back around over here, 12 amps, and we have our 6 amps coming in here. So if we have 6 amps and 12 amps meeting back up at this node down here, then how many amps must be in this wire? Well, that would be 6 plus 12 would be 18 amps, right? So this 18 amps then comes back and meets up with the 4 amps, and there we go. We have our 22 amps back. So we know that the source current, the source or the total current of the circuit is going to be the sum of all the branch currents, right? All right, so perfect. So we basically, if it asks you for the total current, you could just do it like that, right? You would just find, you know, the voltage drop is going to be the total voltage divided by the resistance each branch, and then just add them up. Okay, alternatively, we could use the equation like we did for the series circuit, right? So let's go ahead and do that. So instead, what we're going to want to do is combine all of our resistors together into one resistor. So we're going to go to page 7 on our reference sheet, and it says right there, resistors parallel. It gives us the formula RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And you can do this for as many resistors as you had, right? So we have 3 resistors. So if we do that, we're going to do RT. We're going to go to our calculator. If you're using the TI-36X Pro, you're going to hit the fraction button that is right above the number 7. You're going to put 1 on the top. You're going to hit the down button, the down arrow, and then you're going to hit fraction button again. Once you hit fraction button again, you're going to do 1 over 3. So I'm going to go 1 down 3. I'm going to hit over to the right. Then I'm going to hit the plus sign. Then I'm going to hit fraction button one more time. I'm going to do 1 over 2. So I go 1, go down, hit 2, hit right arrow, and then I'm going to hit plus one more time, and I'm going to hit fraction button again, and I'm going to do 1 over 1, right? 1 over 1 is just 1. If you saw that, you could just do plus 1, but that's fine. And then I hit enter, and what comes out on my calculator is the resistance, total resistance of this circuit is 6 over 11. Well, we don't usually want to work with fractions like that, so I'm going to hit the fraction button, which is right above the enter button, and it is a repeating decimal, so it's 0.54, 0.54, 0.54, dot, 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 dot. So ohms, right? And that is in ohms. So if I notice, this is a low resistance, right? What is the value of my lowest resistor that I have in the circuit? So I've got these 3 resistors. What's the lowest resistor? Well, it's the 1 ohm resistor, right? So if I notice, my total resistance here is lower than my lowest resistor. And that will always be the case with a parallel circuit. The total resistance of a parallel circuit will always be lower than the lowest resistor. If it's not like that, when you do your calculation, you probably messed up somewhere and did a typo. So we know that this is going to be the total resistance, just like we did before, is going to be 0. Like we did with the series circuit, 54 repeating ohms, right? So could I find my total current? It's not giving me all the branch currents, it's just giving me the total current, or the source current, as sometimes it's referred to. So, perfect. So what am I going to do? One more time, I'm going to use Ohm's law triangle. So do I know my voltage drop from here to here? It's 12 volts. Do I know my current? No, that's what I want to find, but I do know my resistance is 0.5454 repeating. So what do I do? 12 divided by 0.5454. So on my calculator, I hit 12, then I hit divided by, then I hit second, which is the top blue button, answer, because that will pull most of that decimal down. and it comes out to obviously be 22 amps because we've already solved for that before. So the total current is 22 amps. So you can do it either way. Again, I do prefer the one where I can just find the branch current each time, but that's totally up to you. It is helpful because sometimes a question might ask you what's the current in that wire, and if you do each branch, and I think it's just a little faster. Perfect. So there is one last thing that we're going to discuss. If you happen to get lucky and all of the resistors in a parallel circuit are the exact same value, like this case, they're 12, 12, and 12, then we know we can use this shortcut method, and that's on page 7 as well. It says parallel shortcut. So let me just ask you a quick question here. So from the last question we have, what do you think the total resistance will be? Do you think it'll be higher than 12 ohms? Or do you think it'll be lower than 12 ohms? So hopefully you said it should be lower, because the total resistance of the circuit is always going to be lower than that lowest resistor. And in this case, since they're all 12, it's going to be lower than 12. The shortcut method is pretty quick and easy, so I just take the value of one of the resistors, right? So that value is 12. This only works if they're all the same, right? And I just divide by the number of branches. Well, how many branches do we have? 1, 2, 3. So 12 divided by 3 is 4 ohms. And is that lower than the lowest resistor? It definitely is. So we did it correctly, or that's at least one check, right? Okay, so another question that comes up a lot is, there's two questions in here. Let me just ask you this. Here's a circuit. This is a new circuit, not this circuit anymore. The total resistance of this circuit, it is a parallel circuit, is going to be, let's just make it 3 ohms. All right. It is parallel. And it is, and it does have 5 branches. So 5 branches, and it is also parallel. All right, so knowing the shortcut method, what do you think the total what do you think the value of one of the resistors is? So let you think about it for a second. One quick question before you start thinking about it. This value, this total resistance, is this going to be lower than the value of one of the resistors or higher? Right, this value should be lower, right? All right, so I'll give you another second to think about it. All right, so this eraser is taking a while. So perfect. So if you understood that, we basically just we take one resistor and divide it by the branches, right? So the resistance total is equal to that one resistor. That's what we want to know, the one resistor. But we do know that there's 5 branches. And we also actually know the total resistance is 3. So with simple algebra, I can just solve this, multiply by 5, multiply by 5. 5 times 3 is 15 ohms. So again, basically what we'd be looking at, 1 branch, 2 branch, 3 branch, 4 branch, 5 branch, 15 ohms, 15 ohms, 15 ohms, 15 ohms, 15 ohms. Well, now if I asked you, hey, I've got a parallel circuit with 5 branches, each branch has a 15 ohm resistor, can you find the total resistance? Well, I would use the shortcut method. I'd take the value of 1, 15, divided by 1, 2, 3, 4, 5, and that would be 3 ohms.